Good morning, professors. I'm Fong Lun from Buddhish College, and it's my honor to be here today to present on the topic of investigation on the Erdos-Straus conjecture. First, we will have introduction with ideas. This is an unsolved problem about Egyptian fractions, and is a question of the existence of sum of three Egyptian fractions. As we can see, 1 over n, 2 over n, and 3 over n, they all can be expressed as the sum of three Egyptian fractions. But then how about 4 over n? That's the question we want to discuss on. Our starting point is to express 3 over n as the sum of two Egyptian fractions. And we are inspired by the length formula and physics, and we construct a geometric model and in this figure, and by this model we can prove theorem 4.1. That is about cutting a unit fraction into two parts. And from this we can prove theorem 4.2, which is about the existence of solutions while expressing 3 over n as the sum of two Egyptian fractions. Then we move on to the amended Erdos-Straus conjecture. And this version points out that it is enough for us to consider while n is a prime, because when n is a composite number, that is n equals to pq, and 4 over 3 can be expressed as sum of three Egyptian fractions, then n also satisfy the requirements of this conjecture. So without notification, we will consider this amended conjecture in the remaining part of the paper. Next, we will start with geometric approach from a book. The book Advanced Euclidean Geometry has inspired us to construct a geometric model about this conjecture, using the relationship between radius of inscribed circle and the radius of external circles of a triangle. And so we put this relationship onto a coordinate plane with P as the radius of the inscribed circle, and assuming that K is smaller or equal to K1 and K1 is smaller or equal to K2. And using geometric tools, perpendicular distance formula, and half angle formula of tangent, we can express K1, K2 in terms of M, P, K, which is theorem 5.2 and 5.3. Please be noted that M squared is a factor of PK squared from the proof of theorem 6.2. From the previous theorems, we have some algebraic and geometric results, but we assume that P is a odd prime, because when P is even prime, that is P equals to 2, we have only one unique solution. Here we will present algebraic results of this we have done. They are theorem 6.1, theorem 6.2, theorem 6.3, and theorem 6.4. And they will be used for several times in the theorems later on. Then we will present our geometric results. But before we start, I would like to give amendments to the definitions of the report, which is about the definitions of Heron triangle and rational right triangle. And their definitions are as follows, and they will be used in chapter 6, theorem 6.5 and 6.6. That is the geometric results. And please be noted that here m is a natural number and is a factor of 2k, and we can construct a Heron triangle like this, but it is not a rational right triangle. Then we have some solutions of the conjecture. That is theorem 7.1, theorem 7.2, theorem 7.3, and theorem 7.4. They are about some special solutions of the conjecture. And please be noted that from now on, we can consider the case when P congruent to 1 mod 4 in the following theorems. Then we will give two new theorems, and for as follows. And they are talking about when we consider a special H such that satisfy the above requirements, then the solutions of this conjecture exist. And we will, for H is even, we only consider the simplest case H equals to 2. And this is the other new theorem. And here, also, this page is to give out the requirements while we want solutions of this conjecture exist when we are assuming m squared equals to hk and m squared equals to up. And especially when h equals to 2, then when the last digit of a prime is 3, the solution of this conjecture exists. And here we will give some examples using the previous 2 pages. They are when p plus 1, p plus 2, p plus 4, and p plus 8. When they contain a special form of vectors, the solution, the conjecture has solutions. We have also done some research on the cases suggested by other papers as follows. And we use Excel to find the solutions of the Erdos-Straus conjecture by substituting different xy or ab. Then we will suggest the extension of this conjecture. The standard version is very similar to our formula proved in theorem 5.2. Just replace 4 with a positive q. And we are going to give an example of extension when q equals to 5. And in this example, we will demonstrate how this formula can help us find most congruence of P where each value has at least one solution in the extended conjecture. The main point of this proof is to take M as a special number such that the denominator can be cancelled out, like the 2 when P congruent to 3, and the denominator 3 and denominator 1 when P congruent to 4 or 2 mod 5. After that, we are going to introduce a new approach using the technique of solving Diophantine equations. But the procedure is a little bit long, so I will point out the main point of this technique. And if you are interested, you can ask me later. The main point is we reduce this conjecture into 2 Diophantine equations as follows. And we solve these Diophantine equations, letting this equation is a combination of a linear Diophantine equations and quadratic equations. That is, we let b equal to x plus y and c equals to xy. Then we solve them individually, and we can get some new results. And I can show a picture which is talking about the example. The reason why I introduced this new approach is that the approach can analyze solutions that we have known on primes. Unlike previous approach, which mainly focus on the special solutions, this approach gives a general observation. Although we cannot solve this conjecture, we can still observe some patterns through this approach. For example, if some of the variables have special values, like as you can see, some of the solutions contain t equal to 0, and we will then this solution is a special one. And the solutions that with no variables with special values, like when p equals to 2521, and it contains many, we will call these solutions a non-trivial one. And the prime 2521 indicate has many non-trivial solutions. And this indicates that 2521 is a very tricky prime to solve in this conjecture.